Section 6.4 is rational exponents. I can simplify expressions with rational exponents. Big ideas here. A radical expression can be written in an equivalent form using a fractional or rational exponent instead of a radical sign. In order to do that here, we're going to take our index number and make it our denominator. Our exponent stays the top part. So here the nth root of x equals x to the 1 over n power, as long as n is positive. Like the radical form, the exponent form indicates the principal root. The nth root of an expression that contains an nth power as a factor can be simplified. So if n is odd, we take it down to just x. If n is even, it's the absolute value of x. And again, sometimes we don't need the absolute value bars depending on what we have, but it's still always going to be the absolute value of x. Sometimes if we square it, though, we get positive anyway and don't have to write them. So in example 1 here, we're going to simplify the expression. 216 to the 1/3 power, we can rewrite. I'm going to take my base as my radicand. My exponent is becoming my numerator. Okay, so that stays a 1. And my denominator becomes my root. So 216 to the 1/3 power is the cubed root of 216 to the 1st power. And again, we don't need that 1 there. Now, I'm looking for groups of 3. 216 is 2 times 108, which is 2 times 54, which is 2 times 27, which is 3 times 9, which is 3 times 3. If you happen to know that that's going to be 6, that's fine. If you don't, though, break it all the way down, and now look for our groups. I have one group of 3 2s. I have one group of 3 3s. And I have nothing left, so all I get here is 6. And because it's a cubed root, we don't put any plus or minuses or anything like that. Same idea here, but before we do that, we're going to take, and since we have the same base, we're multiplying powers with the same base, and that means that we can add our exponents. Half plus a half is 1, which is just 7. If we wanted to, we could have switched these over to square roots. We take our base as our radicand, our numerator as our exponent, our denominator as our root. Same idea here, base, exponent, root. And we don't need the 2 with square roots, but we can. So because they're both squared, we can take 7 times 7. We have one group of 7s that comes out as a 7. Or we can take the square root of 49 to get to 7. So lots of options there on that one. On C, we don't have as many options here because it's not written in the same format. So what we have to do first of all is I'm going to rewrite this as 5 times 25, which is 5 times 5. I'm trying to get my base to be a 5 so that I can combine my exponents. So here, I have 5 cubed instead of 125, and that's still being raised to the 1/4 power. Now, our power rules state that power to a power means I multiply my exponents, and I get 5 to the 3/4. Okay, now when I'm multiplying powers with the same base, I keep my base and add my exponents. I have these rules up in the very back corner of my room on the tan wall closest to the blue wall, the last 3 posters. When I add there, I get 5 to the 1st power, which is just 5. Okay, so the idea here is that we can combine our roots and reduce things as we go. We also could have split this up to be the 4th root of 125, which we could have broken down into 5 cubed 4th root, and then multiplied our values together. So the 4th root of 5 times the 4th root of 125, which we said is 5 cubed, and then gotten here as well. So whether we switch to radicals or just combine our exponents doesn't matter to me, as long as our bases are the same. Go ahead and pause here and give these a try if you'd like. So 64 to the 1/2 power means we're going to take 64, square root, numerator is our exponent. So the square root of 64 is 8. If we're not sure, though, we can break 64 down. And we want groups of 2. 1, 2, 3 groups of 2, 4, 8. So that works as well. Here we have the same base, so I can add my exponents and just get 11. We also could have taken the square root of 11 times the square root of 11. 1 for our exponents, 2 for our indexes. Since they're the same, we can multiply 11 times 11. Group of 2 comes out as an 11. For this one here, it's a little bit different because our bases aren't the same. So on the last one, I split them up so that we could get comparable bases, but here I'm going to do it with the roots. So I'm going to take the 3 for my base to be my radicand, the numerator is my exponent, and the 2 for my index, which again, we don't have to write the 2, I just did there to show you. Same idea here, radicand, exponent, index. Since I have the same index, I can write this as 1 and take 3 times 12 with the square root, which is the square root of 36, which is 6. And if you weren't comfortable with that, we could have broken it down into its pieces. We need groups of 2 because of our index. 2 times 3 gives me 6. Now, if we look at the take note on page 382, it's the same idea here. The only difference is now we can have our numerator be something other than 1. So instead of having a to the 1 over n power equals the nth root of a, we can take a to the m over n power. The denominator still stays our index, but the numerator becomes our exponents. We could also write that as the nth root of a to the m power. It doesn't matter whether our exponent is inside or outside, it's still going to give us the same result. So we're going to write these in radical form. My base becomes my radicand. My numerator, see how it's raised up higher? It stays raised up higher as my exponent. And my denominator becomes my radicand. So here I have the 7th root of x cubed. In the second part here, I'm going to rewrite this as a fraction. So 3.5 over 10, 1 decimal place gives me 1, 0. 35 over the 10, if I divide by 5, gives me 7 over 2. So this is the same as y to the negative 7 over 2 power. Now, in order to make this a positive exponent, we move it to the denominator, make it positive, and our numerator becomes 1. Okay, in order to make our exponent positive, we move it to the opposite part of our fraction, so top to bottom or bottom to top, and change the sign. So right now I have 1 over y to the 7 over 2. My base is going to become my radicand. My exponent stays raised, my numerator stays raised like an exponent. My denominator becomes my index. And if I look here, if I have 7 y's, I can take 3 groups of those out. 7 divided by 2 is 3, remainder 1. So I'm going to have 1 over y cubed times the square root of 1y left, my remainder. And we never want to have a radical in our denominator. So I'm going to go ahead and multiply by 1 more y as a square root of y, top and bottom. Now I have a group of 2 with an index of 2, so I can take that out. Y cubed times y in my denominator. In my numerator, I just have square root of y. And now in my denominator, I can add my exponents. So I get the square root of y over y to the 4th power. So a little bit more there because we had the negative exponent, and we can reduce that to take some out. So we had to rationalize it, but same kind of concept there. So to write these in exponential form, we're going to go backwards. I'm going to take my index number, which here is a 2. Okay, make sure we know that. We take our radicand as our base. Our exponent is always raised up, so it's going to stay raised up here. And our radicand, our index number here that goes with our radicand, is going to be our denominator. So a to the 5 over 2. Same idea here. It doesn't matter if that exponent is inside or outside. Here, I can take b. My exponent is a 1. My index is a 5. Index becomes my denominator. And that's raised to the 3rd power. Now, power to a power says I multiply my exponents, which gives me 1/5 times 3 over 1, and gives me 3/5. So again, it doesn't matter if it's inside, like here, or outside, like there. It still just becomes the numerator of my exponent. Now, we're going to go ahead and write these in radical form. Feel free to pause and give these a try if you'd like. First thing I'm going to do is make this positive by moving it to the denominator and making it positive. Now, I have the 8th root of w to the 5th power. Denominator. And since my numerator is already raised, it stays raised like the exponent. We never want to have a denominator in our radical or a radical in our denominator. So I need to rationalize this. I need a group of 8 because of my index. I have 5, that means I need 3 more. So I'm going to multiply by the 8th root of w to the 3rd power. In my denominator, that gives me w to the 8th power, and I need a group of 8, so just a w. Perfect, we have no more radical. And in my numerator, I have the 8th root of w to the 3rd power. For the second one here, I'm going to rewrite that as a fraction. So instead of having 0.2, I'm going to get rid of my decimal. There's 1 decimal place afterwards. So I'm going to write it with 1, 0, and then reduce if we can to 1/5. I have w to the 1/5 power. Remember, our denominator becomes our index, our base becomes our radicand, and our exponent comes from our numerator. Here, just a 1, which we don't need. We're the 5th root of w. Now, to write these in exponential form, we take our base. The exponent, since it's already raised, goes on top in my numerator. My index becomes my denominator. So x to the 3/4. Here we take our base to the 5th index, which is our denominator. And my exponent on my y right now is a 1. And that whole thing is raised to the 4th power. So power to a power means I'm going to multiply my exponents. And I'm going to get y to the 4/5. If you want to skip this middle step and go right to the 4/5, that would be okay with me. In example 3, it says, Kepler's third law of orbital motion shows how we can approximate the period p in Earth years it takes a planet to complete one orbit of the Sun. Use the function p equals d to the 3/2 power, where d is the distance from the planet to the Sun in astronomical units. How many Earth years does it take Mars to orbit the Sun? So if we look on page 383 at the diagram there, it looks like from the Sun to Mars is 1.52 astronomical units, or AUs. And it says that d is that distance in AUs. So this is going to be my d value. I substitute that in, 1.52, raised to the 3/2 power. When you type this in your calculator, guys, you need to either use the fraction key, 3 fraction 2, or put it in parentheses if you're going to use just division. And we should get 1.87 years, Earth years. So please type that in your calculator and make sure you can get there. Make sure you type in that exponent right. Again, either use the fraction key or type it in parentheses. And that's all I have for the first half. We'll continue in a second video.